So in section 7.6, we're going to be looking at a new type of function. We're going to call that exponential functions. A couple different goals with those. Going to be able to evaluate and graph them. Just like what we did with line equations back in the first semester, we're going to do the same thing with our exponential functions now. And I know a lot of times I skip this first question, but I think in this case it's pretty helpful to see the difference. Let's say we have a soccer team and we are going to follow one of these two practice plans. The idea is we want to see out of the two plans that are listed, which one's going to give us more total practice time over the first 4 days and which one over the first 8 days all put together. And I've listed those answers already off to the side, but if I list those practice schedules out one at a time, first plan says to practice 5 minutes the first day and then add 1 minute of practice for every day after that. Second plan, if we're trying to compare, we only start with a 1 minute practice on the first day and then double that, so it says twice the amount of practice, and take that pattern going forward. So every day is twice as much as the day before. So if I'm trying to compare the first 4 days, it looks like on the fourth day, they both have an 8 minute practice, but over the first 4 days combined, it looks like plan 1 beats plan 2, with every day before that being just a little bit longer. If I'm trying to look at that pattern over all 8 days though, so this is looking at, looks like plan 2 now, obviously towards the back half of that practice schedule, these practices start to get a lot longer under plan 2 than they were in plan 1. And that's going to be a pretty consistent pattern that we're seeing in this section. So plan 1, if we remember back to, again, first semester, this was basically our linear pattern. Start off with an initial value and then just increase by the same amount every time. We see a similar pattern on plan 2, but this is going to be an exponential pattern, and that's going to be, again, focus of this section. So a few things to know about our exponential functions. First thing is that, again, they're going to have different patterns of growth compared to linear versus what we see now with exponential. And that means if we have different patterns of growth, we're going to have a different type of function. And that's where we get our new section from. So some functions model initial amount that is repeatedly multiplied by the same positive number. In that practice example, that number was 2. I keep multiplying by 2 every time if I want to double the amount of practice. And when I'm making rules for this, and we want to think a rule is just an equation, in that equation, our independent variable is going to be an exponent. And that's something we haven't seen before, but we illustrate that in our next little box here. So any exponential function always going to follow this pattern. So an exponential function is a function of this form, and that's going to be y equals a times b to the x. That's your important rule. That's the one thing to take from this section, is to know how to use this function and where these pieces come from. So I'm just going to describe a as, a lot of times you're going to see the word initial value, but we can just say starting value for our function. And that means if I'm trying to graph something like y equals 2 to the x power, again, here are variables and exponent, we're going to see a graph that looks something like this. So we start the graph, it looks like actually at the point 1, because in this equation, it doesn't look like there's an a at all. That's like saying 1 times 2 to the x power. We start the graph still at our initial value, and that's where we use this b term as our growth factor. Just like in that practice schedule, it looks like if 2 is being raised to an exponent, that 2 is a growth factor, means every number after that, I keep doubling and multiplying by 2. So if we started at, again, 1, that was our initial value. If I want to go to the next x value, so if I go 1 space over, now if I double, I'm at 2. And if I want to go another x space over, I'm doubling again, so already I'm at 4. So following that sort of pattern is going to be giving me an exponential function. Again, just 2 things that we have to keep track of is where did I start and what pattern am I taking from there. So the only difference if I make that function negative is that's like starting with initial value that's -1. And if I keep multiplying by 2, I'll just be getting a bigger and bigger negative value. So I'm going to be headed downwards with that graph. And we'll also be looking at this a little bit more in our next section, but I could be dealing with not even growth, but we'd call this eventually decay. If I multiply by 1/2 every time, it's going to keep multiplying, but multiplying by half is going to make those numbers smaller and smaller. So I'm going to get really close to 0. We actually never touch 0, but that function is going to be decreasing as I move over to the right instead of increasing. And if I make that function negative, again, just like last time, looks basically like a mirror image. So first thing we're going to be asked to do, though, is we're going to be asked to tell the difference. And that was looking at things we've seen before with our linear functions. Some x values in a table, again, are going to have a common difference, right? Increase by the same amount every time. And if all the y values also have a common difference, we've seen that pattern before, we just called that linear. So if all of them have a common ratio instead, that's our new term, that's now going to be an exponential function, not a linear function. So I think I'm just going to look at one example of each of these, and I think it's going to be up to you guys to see if you can tell the differences on the others. I'm going to look at, I think, A and C, and if you guys want to try B and D and think of where I'm getting those from, that's a good question to practice. In A, we get this in a table. It looks like all the x's are increasing by 1, and we can make note of that common difference. And if I'm looking for the change in the y values, it looks like they're always adding 2, so that would make this a linear function. We don't need an equation for it. We just know that if I'm increasing by adding the same amount every time, that's going to be linear. And again, if you guys were to try B, you would see that you're not adding, instead you're multiplying. That makes that exponential. So for C, let's say if I get this in a rule instead, so if I just get an equation, we just need to know that this matches our pattern. This is our A times B to the x pattern. That's going to be exponential. As soon as I see that that x is not a coefficient, if that's an exponent instead, that's where the name comes from. That x as an exponent makes this entire thing an exponential function. And we could still see this if we're to make our own table. Let's say if I start with 0, 1, and 2, that's going to be a pretty common start to a lot of these. I could start by just substituting those in one at a time. 3 times 6 to the 0th power. Remember, x was our exponent. From our previous section, we know everything raised to the 0th power is going to make 1. So that's like saying 3 times 1 just gives us 3. And remember, that just matches our starting value. When x was 0, we're always going to get that a term. So let's say if I plug in 1 for x, 3 times 6 to the first power is just like saying 3 times 6, and that just gives us 18. If I take that as third step, so if I plug in 2, I would get 108 already for a y value. So sometimes it's harder to tell from a table, 3, 18, 108. Obviously, we're not adding the same thing every time, so we know it's not going to be linear. But if we want to check and make sure that it's exponential, I could always go backwards and just divide. If I take 18 divided by 3, that gives me a factor of 6. If I also do 108 divided by 18, it gives me a factor of 6. It means to get each value in our table, we just keep multiplying times 6. Remember, that's what that growth factor is for. If I keep multiplying every new number by 6, that's going to give me the next value in the sequence, and that's when why I'm raising that value to an exponent. We see a different pattern again if you were to try D. We see that's actually linear. And notice just by looking at the equation, x is not an exponent, so we wouldn't even really need a table. We know we're not going to have an exponential function. So in some cases, again, what we're asked to do first is to evaluate our exponential function. And we're not going to focus too often on making our exponential functions ourselves. So this is giving us a word problem as an initial population of 20 rabbits, and it's also telling us that it triples every half year. So initial population of 20, that's telling us, first of all, that that's basically like our starting value. So starting with a population of 20 rabbits, if we're then told that they triple every half year, that's basically a growth rate. So if I'm trying to think of that as my B factor, again, that's how much I'm multiplying by every time. That was tripling. So it gives us the function to work with. And the one thing to watch out for if we're asked how many rabbits will there be after 3 years is that we're actually not using 3 as an exponent. Since this question is focused on x in terms of half years, 3 years is actually 6 half years. So a little bit quirky on this question, but for the most part, we're thinking what value am I substituting? We just want to make sure we're not substituting 3 for x, we're substituting 6 for x. And then if I evaluate, and again, this would be an answer that we could just leave in this form really if I wasn't using a calculator. Don't expect you guys to know 3 to the 6th power, but 20 times 3 to the 6th power is going to give you a lot of rabbits, and that was by, again, tripling that population. We're going to see that that happens a lot with exponential functions. Just by going 6 periods, so 6 half years, exponential growth is a lot faster, so that's already in the thousands in terms of our population. So that's our idea with evaluating is we're going to find out what number we're substituting in. We're given a function, all we got to do is take that 6, plug that in for x, and if necessary, we could use our calculator to get that final answer. So after evaluating, the only other thing we're going to be looking for is graphing. And graphing can work the same way as when we first started graphing linears. If I make a table of values, I'll know where to put those points on a graph. So again, we know we have an exponential function, first of all, because x is our exponent. And we also have, same thing as before, we have a starting value of 2. This time the growth factor actually matches just another value of 2. So without even putting this into our table, when I use the word starting value or initial value, you can think of that as when you're making your linear graphs as just like your y-intercept. So if I know that value is 2, I know this is already going to be this first point on my graph. And I'll just point that out in each graph to start with. Same thing here, we start with the initial value of 2. That's where our y-intercept starts, is just at 2. moving down. If I start at -2 instead, doesn't really change a whole lot, just means that just like with a negative y-intercept, that would be fine as a negative starting value. And we see again the same thing on D. We have a negative starting value, which just means we start our graph with a negative. So that's the first thing to look for in every graph. Whatever your starting value is, that should just go basically as your y-intercept every time. And now that I'm adding in this growth factor, 2 to the x power, could do this a couple ways. You could do it from a table, which I think is the best method if you're still getting used to these. We started at 2, but every time if I want to increase with this growth factor, that means instead of adding 2 every time, I'm making sure to multiply by 2 every time. So multiply by 2, I get 4. Multiply again, I get 8. And again, we could also substitute them in 1 by 1 like we did before. Substitute 0 for x, or 1 for x, or 2 for x, and you can still evaluate each one and get the same solution. So if we know our starting value is at 2, we know that every time if I keep doubling, and we want to make sure too we're only moving by, it looks like 1 over to the right every time. We're only increasing the x value by 1. Every time we do that though, the y value is doubling, so I go from 2 to 4 to 8 already. Don't really have to keep going past that, so I can just list that as continuing that pattern. I want to make sure the arrow still stays there to say that that function keeps going. But we can also imagine if I reverse that pattern, since I'm doubling as I go to the right, I'm really just dividing by 2 as I go to the left. So let's say if I wanted a few more numbers going to the left, I can start at 2 and divide by 2. That just gives me this point here at 1. And then what we're going to see as a pattern is we basically just get closer and closer to 0, because I'd start to be getting a lot more fractions towards this side. So trying that again with another example. Again, if I have same starting value, we're still starting at 2. Only difference here is now I'm using a growth factor that's less than 1. If I use 1/2, it means we keep multiplying by a fraction. So if I start at 2, again, same thing as before, and we can see this again from our table. If I multiply by 1/2, it's really the same thing as dividing by 2. So I would get 1 for my next value. If I keep that pattern going, dividing by 2, I would get another 1/2. And again, this is where we start to see our fractions. And just like our last question, you could think of this pattern also in reverse. If we're basically multiplying by 1/2 as I go to the right, we're doubling our value as I go to the left. So if I start at 2, going back one more step would be 4, and going back a second step would get back to 8. So similar looking graphs. All we did by changing that growth factor from 2 to 1/2 is now we're basically getting smaller and smaller instead of larger and larger. And just looking at these last 2 examples, I think I'll just point out these differences real quick. Only difference was we started with -2 as a starting value. Otherwise, our table is the same. We keep doubling because that growth factor was 2. So if I keep multiplying by 2, I'm just going to get a bigger and bigger negative. And if I take that second pattern, same thing as before, if I multiply by 1/2, I'll see a similar sort of pattern. So I still start at my -2, but now if I keep multiplying by a -1/2, it's going to get me a smaller and smaller fraction, and that's just going to look like almost a flat line on your graph. Same thing as our last question though, we could extend the pattern going backwards. You could even plug in -1 if you'd like for an x value. We'd see that we get -4 for a y value. I could get -8 again for a y value if I go back one more step, and that's just continuing that same pattern. So a big thing to focus on when we're graphing is just what's that starting value. If I start at -2, that's going to be our y-intercept. And then where do I go from there? We want to make sure we're not going up or down by 2. This is where we're multiplying by 2. So -2 times 2, we get -4. -4 times 2, we're down at -8 already. And we're going to see that again a lot with exponential functions. They just increase or decrease a lot quicker than our linears. So just make sure you have these notes filled out, and we'll see if we can add on in class.